Our entire understanding of reality rests on a contradiction. General relativity explains the stars. Quantum mechanics explains the particles. Both theories are flawless. Both are proven beyond doubt, and both are fundamentally incompatible. We've split the universe in half, and no one knows how to put it back together. The first crack in the foundation appeared not in some distant galaxy, but in the glow of heated iron. When 19th century physicists turned their mathematics toward the problem of how hot objects radiate energy, they expected merely to tidy up a few remaining details. Classical physics had already explained the motion of planets and the dance of moons, the propagation of sound and the behavior of light. It was a cathedral of human thought, 2 centuries in the building, and it seemed nearly complete. But when they applied its equations to something as simple as a glowing poker, the mathematics went spectacularly wrong. According to wave theory, any heated object should emit ever more radiation as you move toward shorter wavelengths, pouring out blinding torrents of ultraviolet light, then X-rays, then energies beyond imagining. The equations insisted that every heated body should blaze with infinite intensity, that every fireplace should become an inferno, that the universe itself should have long since burned to a cinder. Yet when scientists actually measured what hot objects radiate, they found nothing of the kind. The ultraviolet emissions were mysteriously, mercifully suppressed, far less than the theory predicted, as if some hidden principle were restraining the flood. The universe was not the runaway catastrophe that classical physics demanded. Something was missing from the equations, something fundamental, and the physicist who would dare to supply it would be forced to commit what he himself would call an act of desperation. The first crack in the foundation appeared not in some distant galaxy, but in the glow of heated iron. When 19th century physicists turned their mathematics toward the problem of how hot objects radiate energy, they expected merely to tidy up a few remaining details. Classical physics had already explained the motion of planets and the dance of moons, the propagation of sound and the behavior of light. It was a cathedral of human thought, 2 centuries in the building, and it seemed nearly complete. But when they applied its equations to something as simple as a glowing poker, the mathematics went spectacularly wrong. According to wave theory, any heated object should emit ever more radiation as you move toward shorter wavelengths, pouring out blinding torrents of ultraviolet light, then X-rays, then energies beyond imagining. The equations insisted that every heated body should blaze with infinite intensity, that every fireplace should become an inferno, that the universe itself should have long since burned to a cinder. Yet when scientists actually measured what hot objects radiate, they found nothing of the kind. The ultraviolet emissions were mysteriously, mercifully suppressed, far less than the theory predicted, as if some hidden principle were restraining the flood. The universe was not the runaway catastrophe that classical physics demanded. Something was missing from the equations, something fundamental, and the physicist who would dare to supply it would be forced to commit what he himself would call an act of desperation. For 2 centuries after Newton, the universe seemed a machine. Know the position and velocity of every particle at one instant, and you could calculate their positions at any future instant. Every orbit, every collision, every falling apple was predetermined, a clockwork cosmos running on rails. But the seed Planck had planted contained something he never expected. His quantization of energy led to a conclusion that shattered the ancient dream of determinism. The universe is not a machine. It is governed by probability and chance. At the scale of atoms, nature refuses to reveal what will happen next. You cannot predict precisely where an electron will appear, or exactly when a radioactive nucleus will decay. The uranium atom in some ancient rock may disintegrate in the next second, or it may wait another billion years. The laws of physics offer no hint as to which future will unfold. Ask the universe a question about an atom's destiny, and it answers not with certainty, but with a cloud of likelihoods, a smear of possibilities, where classical physics had promised a sharp, definite point. The laws of physics no longer speak of certainty, they speak of likelihood. This was a profoundly disturbing revelation. For millennia, philosophers and scientists had assumed that if we knew enough, if we could measure precisely enough, the future would unfold before us like a roadmap. Quantum mechanics destroyed that hope forever. Not because our instruments are too crude or our measurements too imprecise, but because nature itself keeps its own counsel. At its foundations, the cosmos is not a clockwork machine, but a game of chance, and the dice are rolling everywhere, in every atom, at every instant. And yet the deterministic world of Newton somehow emerges from this underlying chaos. The reason lies in the tiny magnitude of Planck's constant. Because this number is so extraordinarily small, the phases of all the possible paths a particle might take spin rapidly and randomly, interfering destructively with one another, canceling out like waves in a storm. Almost every trajectory vanishes in this interference. But one path survives, the path where the phases align, where constructive interference reinforces rather than destroys. That survivor is the path of least action, the very trajectory Newton's equations had described all along. There is no clearer window onto this indeterminism than the decay of a single radioactive atom. Take one atom of uranium and watch it. Quantum mechanics can tell you the probability that it will decay within the next hour, the next year, the next billion years, but it can never tell you when this particular atom will let go. Two identical atoms, forged in the same stellar furnace, sharing every physical property we can name, will nonetheless disintegrate at wildly different moments, one perhaps in a heartbeat, the other outliving the galaxies. Nothing distinguishes them, nothing determines their fates. The classical physicist searches for the hidden cause, the secret difference that decides which atom decays first, and quantum mechanics answers that there is no such cause, that the timing is woven from pure chance at the very bottom of things. This is not our ignorance speaking. It is the world confessing that, at its foundations, it does not know its own future. The clockwork universe was not wrong then. It was an average, a statistical result rising from an underlying bedlam of possibilities. Every quantum particle seems to explore all possible futures before settling into one present. The electron does not simply travel from here to there. It tries every route, samples every possible trajectory, and all those attempted journeys interfere with one another until only the classical path remains, the path that Newton would have predicted, the path of least action. And if this seems too strange to believe, there is a way to see it for yourself. An experiment so simple that it would make Richard Feynman grin with delight. Consider what happens when light strikes an ordinary mirror. You have been taught that it bounces off at an equal angle, that the path of reflection is predictable, orderly, almost boring. But Feynman understood that this orderly behavior is merely the statistical average of countless chaotic possibilities, and there is a way to see those possibilities emerge from hiding. You need only a diffraction grating, a mirror whose surface has been etched with thousands of parallel grooves, like the furrows of some vast and microscopic plowed field. When a beam of light strikes this ruled surface, each groove becomes a new source of reflected waves, and all those sources interfere with one another. The phases of these countless reflected beams spin like innumerable tiny stopwatches, each ticking at its own rate. Most paths produce phases that cancel one another out, destructively interfering into darkness, while only a few, the ones whose phases happen to align, survive and combine into the familiar angle of reflection. The other paths are still there, invisible only because they are being erased by their neighbors. Now comes the revelation. If you cover the regions of the grating that produce the familiar reflected beam, if you block precisely those paths that classical physics says light should take, something impossible happens. The reflection does not dim. Instead, light begins to emerge from portions of the mirror that were dark before, from angles that no simple reflection could ever produce. By removing the canceling paths, you have allowed the hidden paths to reveal themselves, exactly where Feynman's mathematics predicted they would be. The crazy trajectories, the ones that seem to wander improbably across the mirror's surface, are not mathematical fiction. They are real. A colleague of mine, a careful experimentalist by temperament, wondered whether the grating itself was somehow manufacturing these strange reflections, a kind of optical trick, an artifact of the apparatus rather than a revelation about the nature of light. So we tried something more direct. A laser, its beam coherent and unwavering, struck the grating while we carefully masked those regions that ought to have produced the classical reflection. The result was unmistakable. The light that emerged came not from where tradition said it must, but from where quantum mechanics said it might. The apparatus had not changed, only our understanding had. And with that understanding, a question arises that would have seemed absurd to Newton and bewildering even to Einstein. For if light truly samples every possible path through the universe, testing each one, however improbable, then what has happened to certainty itself? The classical physicist believed that nature follows definite trajectories, that cause leads to effect along well-marked roads. But nature, it seems, prefers to explore, and only after exploring everything does it settle, statistically, into the paths we find familiar. In the closing years of the 19th century, a new nation raced toward modernity. Germany, unified barely 2 decades earlier, had become an industrial powerhouse, and in its factories and laboratories, a new kind of light was flickering into existence. The electric light bulb was transforming night into day, and the men who manufactured these glowing filaments faced a question of urgent practical concern. How could they make their bulbs burn brighter, hotter, more efficiently? The problem was economic as much as it was scientific. Every watt of electricity wasted as heat rather than light cost money. Every hour a filament survived meant profits for its makers and cheaper illumination for the growing cities of Europe. To solve it, physicists needed to understand something far deeper than the engineering of glass and tungsten. They needed to understand the very nature of how hot objects radiate their energy into the void, how a glowing filament, not so different from a tiny sun, pours out its light across the spectrum of wavelengths. What they found, when they traced the curves of blackbody radiation, was a pattern both elegant and inexplicable. A heated body emits energy across many wavelengths, some infrared, some visible, some ultraviolet, and when physicists plotted intensity against wavelength, the result was a graceful arc rising to a peak and falling away again. But the equations of classical physics could not reproduce what the instruments recorded. The theory predicted curves that climbed ever higher into the ultraviolet, pouring out infinite energy at short wavelengths, a mathematical absurdity that simply did not happen in nature. The scientists of Imperial Germany had stumbled into a region where the old maps no longer matched the territory, and somewhere in that gap between prediction and observation, a revolution was waiting to be born. Into that gap stepped two young revolutionaries, each grasping a different thread of the same strange idea. Max Planck had proposed that energy comes in discrete packets, but he thought of it as a mathematical trick, a convenient fiction to make the equations work. Albert Einstein, working in obscurity at the Swiss Patent Office, saw something deeper. When light strikes a metal surface, it knocks electrons loose, the photoelectric effect. Classical physics insisted that brighter light should kick the electrons out harder, but experiments showed otherwise. The color of the light alone determined the energy of the ejected electrons. Dim blue light could scatter them violently. Bright red light, no matter how intense, could not pry them loose at all. Einstein realized that Planck's quanta were not mere mathematics, but real physical entities, particles of light, later called photons, each carrying a packet of energy proportional to its frequency. One high-energy blue photon could do what 1,000 low-energy red photons could not. The photoelectric effect, inexplicable for decades, suddenly made perfect sense. Niels Bohr, contemplating the hydrogen atom, faced an equally baffling contradiction. According to classical electromagnetism, an electron orbiting a nucleus should radiate away its energy and spiral into collapse within a fraction of a second. Hydrogen atoms should not exist, yet here they are, the most abundant atoms in the cosmos, stable and enduring. Bohr proposed that electrons occupy only certain permitted orbits, discrete rungs on a ladder rather than a continuous slope. They can jump between these rungs, emitting or absorbing photons of precisely the right energy, but they cannot slide down through the forbidden zones between. The quantized atom predicted with uncanny accuracy the spectral lines of hydrogen. Einstein and Bohr had extended Planck's insight in two directions at once. Light itself comes in discrete photons, and the electrons orbiting atoms are quantized into discrete energy levels. The same graininess that had saved physics from the ultraviolet catastrophe was now illuminating the fundamental nature of light and matter. But accepting that light comes in packets meant accepting something that would take decades to fully understand, and that many physicists, even today, still have not grasped. Einstein proposed something that must have seemed at first almost absurd, that light consists of discrete packets of energy, which we now call photons, each one carrying an amount of energy exactly proportional to the frequency of the light. The relationship is precise and simple. Energy equals Planck's constant times frequency. A photon of violet light, with its high frequency, carries more energy than a photon of red light. A photon of ultraviolet carries still more. This explained, with elegant clarity, why the photoelectric effect had been so baffling. When light strikes a metal surface, it does not behave like ocean waves steadily eroding a beach. It behaves like rain falling on a roof. Each photon is a discrete drop, and only when a drop carries enough energy, when its frequency is high enough, can it knock an electron loose. Intensity merely increases the number of drops. Frequency determines whether any electron can be knocked free at all. Einstein had not only solved the puzzle, he had fundamentally reconceived the nature of light. Einstein himself could never fully accept what his insight had unleashed. The same man who had shown that light behaves like particles could not bring himself to believe that particles might also behave like waves, that certainty might give way to probability at the heart of nature. He would spend the latter decades of his life arguing against the very theory his photons had helped to create, famously insisting that God does not play dice with the universe. But the road from Einstein's photons to our present understanding of quantum mechanics has been longer and stranger than most people, even most physicists, fully appreciate. I have sat with colleagues who have spent years calculating with quantum wave functions, physicists of genuine accomplishment and insight, and I have discovered, to my surprise, that many of them do not know Bell's theorem or have misunderstood what it actually proves. I recall one conversation in particular. A theoretical physicist who had published extensively on quantum field theory looked at me with frank astonishment when I mentioned Bell's inequality. He had simply never encountered it in his training. Bell demonstrated in 1964 that the predictions of quantum mechanics are incompatible with any theory in which particles have definite properties before measurement, and in which those properties are determined locally. The universe, Bell proved, is either non-local, allowing instantaneous influences across arbitrary distances, connections that respect no limitation of the speed of light, or it does not contain definite properties until those properties are measured, which is to say that the act of observation somehow calls forth reality from potentiality. There is no third option. This is not a matter of interpretation. It is not philosophy. It is mathematics, as rigorous and unavoidable as any proof in all of physics. Yet somehow, this result, one of the most profound discoveries of the 20th century, remains unknown to many who practice the very theory it illuminates. The equations predicted perfectly, but prediction, it would turn out, is not the same as understanding. Prediction is not understanding. Tim Maudlin, a philosopher who has examined the foundations of quantum mechanics with patient rigor, has drawn attention to something troubling. The quantum recipe, the practical procedure that has served physicists for a century, contains a gap that the textbooks rarely acknowledge. Consider the detection screen in a typical quantum experiment. In diagrams, it appears as a simple surface where particles land and reveal themselves. But any actual screen is made of atoms, countless billions of them, packed together with a particular thickness and composition and response time. Should a particle register at the front surface or somewhere within the material, How long after arrival does detection occur? The theory offers no guidance. It cannot model the physical detector from its own principles, nor can it predict when precisely a particle will arrive. These essential features must be inserted by hand, through approximation and guesswork drawn from outside the theory. There is a peculiar circularity in this. To make a prediction, quantum mechanics requires that we specify what counts as a measurement, where and when the fog of possibilities condenses into a fact. But a measuring device is itself a physical object, made of the same atoms as everything else, and so it too should be governed by the very equations we are trying to apply. If we take the theory at its word, the detector ought to enter a superposition along with the particle it measures. Pointer needles pointing in many directions at once, ink dried into many patterns simultaneously. Yet we never observe such a thing. We see a single needle, a single mark. Somewhere the chain of superpositions is severed, and the theory does not tell us where. We are forced to draw a line by hand, to declare, without justification from the mathematics, that on this side lies the quantum, and on that side the classical. The most accurate physical theory ever devised cannot, on its own terms, describe the instruments that test it. This incompleteness was not merely technical. It would lead directly to one of the strangest claims ever made in the name of science. The measurement problem led the early founders of quantum theory to a conclusion that still unsettles us. Bohr and Heisenberg argued that objective reality does not exist until it is observed. Before the measurement, the electron is not merely hidden from view, waiting in some definite place we happen not to know. It occupies no single place at all. It exists in a superposition, a sum of possibilities, and only when we look does one possibility become actual. The universe, in this view, is not a great machine running independently of us, its gears turning whether we watch or not. It is a kind of participatory drama in which the observer calls forth existence from the fog of probability. It was Erwin Schrödinger, one of the very architects of the theory, who found this conclusion so absurd that he devised a thought experiment to expose its strangeness. Imagine, he said, a cat sealed inside a steel chamber, hidden entirely from view. Within the chamber sits a single radioactive atom, and beside it a detector, a hammer, and a flask of poison. If the atom decays, the detector trips, the hammer falls, the flask shatters, and the cat dies. If the atom does not decay, the cat lives. Nothing could be simpler in its mechanism. But recall what quantum mechanics insists about that atom. Until it is observed, it exists in a superposition, decayed and undecayed at once, a sum of both possibilities. And if the atom's fate is genuinely undecided, then so too is the cat's. The mathematics, followed without flinching, describes a cat that is neither alive nor dead, but both. A grotesque smear of two contradictory realities, suspended until someone lifts the lid and looks. Schrödinger did not intend this as a description of how the world works. He intended it as a reduction to absurdity, a way of shouting that something must be wrong with a theory that permits such monstrosities. Yet the puzzle has refused to die. Where, exactly, does the superposition end? The atom is surely quantum. The cat is surely classical. Somewhere between the single decaying nucleus and the living, breathing animal, the fog of possibilities must condense into a single fact. But the equations mark no such boundary, and they offer no line where the quantum blur becomes the classical certainty we experience. This is the measurement problem in its most vivid and disquieting form, and a century of brilliant minds has not dissolved it. Imagine that each particle carries with it a tiny stopwatch. The hand rotates steadily as the particle moves through space and time. This rotation is the quantum phase, an internal clock that keeps perfect time with the journey. Along each possible path, the stopwatch runs at a slightly different rate, its hand arriving at a different final angle. To find the probability that the particle reaches some point, we must sum over all paths, adding their contributions like ripples from stones dropped in a pond. Buried in the mathematics is a hidden connection to the classical world. When we calculate the phase changes along each tiny segment of a particle's possible path, we find that the stopwatch's spin rate is determined exactly by the classical action. The same quantity that governs the trajectory of every falling stone and every orbiting planet controls how rapidly the quantum phase rotates. The classical world emerges from the quantum through this correspondence. The path of least action survives because its neighboring paths all spin in the same direction, their phases aligned, adding rather than canceling. And this ancient principle, that nature chooses the path of least action, can be glimpsed even in something as simple as a lifeguard racing to save a drowning swimmer. Consider a lifeguard who spots a drowning swimmer some distance from shore. She could sprint straight for the water and swim directly to the victim, but she runs faster than she swims, so this route wastes precious time in the slow medium. She could run far along the beach to minimize swimming, but this adds distance overall. The optimal path lies between these extremes, following the same rule that light obeys when passing from air into water, the same rule that governs the arc of a thrown ball and the curve of a planet's orbit. Nature has been finding the path of least action since long before there were minds to notice. The mathematics is precise. The sine of the angle the lifeguard's path makes with the shoreline before entering the water, divided by the sine of the angle after, equals her running speed divided by her swimming speed. Run 4 times faster than you swim, and the geometry of the fastest path is fixed. This is not approximation. This is exact. In the 2nd century, the Greek astronomer Ptolemy measured how light bends when passing from air into water. Anyone who has ever reached for a stone at the bottom of a clear stream knows the phenomenon. The stone is not where it appears to be. A stick partly submerged seems broken at the surface. The bending was obvious. The explanation was not. Why should light change direction when it crosses from one medium into another? Then, in 1662, Pierre de Fermat proposed an answer of disarming simplicity. Light, he suggested, takes the path of least time, not the shortest distance, the shortest time. The two are equivalent when speed is constant. But when light slows in water, the shortest time path bends toward the perpendicular, exactly as the lifeguard's optimal trajectory bends. Fermat had discovered a principle that would extend far beyond optics, a principle governing the shape of motion throughout the cosmos. Yet even as such principles revealed the hidden order in nature's behavior, other mysteries were accumulating, conflicts between the very foundations of physical law. One such conflict emerges from the most extreme objects in all the cosmos. When a massive star exhausts its nuclear fuel, it can collapse so completely that space-time curves into an infinitely deep well, a black hole, from which nothing, not even light, can escape. Stephen Hawking discovered that such objects are not truly black. Through an exquisite interplay of quantum mechanics and gravity, they radiate energy, slowly evaporating over aeons. But here lies the puzzle. Quantum theory insists that information is never truly destroyed. It may become scrambled beyond all recognition, dispersed into the finest structure of physical reality, yet it remains conserved, preserved somewhere in the universe's accounting. But if a black hole evaporates entirely, what has become of all the information about everything that ever fell inside? Has it simply vanished from existence? The prospect tears at something fundamental. Physicists have proposed mechanisms by which information might be encoded in the outgoing radiation and thus preserved. Partial solutions, but ones that feel somewhat makeshift, not fully satisfying. To feel the full weight of the paradox, imagine dropping an entire library into a black hole. Every book, every manuscript, every record of human thought. Classical intuition says the information is lost the instant it crosses the horizon, sealed away forever. But quantum mechanics forbids even this. In the quantum world, the present state of things always contains, in principle, a complete record of the past. Run the equations backward, and the history unfolds in reverse, every detail recoverable. Information may be shuffled, encrypted, smeared across the whole of a system, but it can never be erased. This is not a matter of practical difficulty. It is written into the deepest structure of the theory. And yet Hawking's radiation, as he first described it, carries no memory of what fell in. It emerges featureless, thermal, the same whether the black hole swallowed a library or a lump of lead, determined by nothing but the hole's mass, charge, and spin. If that radiation is truly all that remains once the black hole has evaporated to nothing, then the information is gone, and quantum mechanics has been violated in the one place we cannot follow to check. Here, two pillars of physics press against each other with their full weight: the quantum insistence that information endures, and the gravitational verdict that it may vanish beyond an horizon. Something must give. Either the radiation secretly encodes what fell in correlations too subtle for Hawking's original calculation to reveal, or one of our sacred principles is wrong. Decades of the finest theoretical work have been poured into this crevice, and while most physicists now believe information does escape, no one can yet say exactly how. This black hole information paradox is one face of a larger tension between our theories, and the contradictions only deepen when we examine the heart of quantum mechanics itself. Nowhere does the strangeness of the quantum world announce itself more defiantly than in the phenomenon Einstein derided as spooky action at a distance. Take two particles and allow them to interact, then send them flying apart, one to a laboratory on Earth, the other, in principle, to the far side of the galaxy. Quantum mechanics insists that these two particles may remain bound together in a single shared state, a condition we call entanglement, in which neither particle possesses a definite property of its own. Measure one, and you instantly learn something about the other, no matter how vast the gulf between them. Einstein could not abide this. Together with Boris Podolsky and Nathan Rosen, he argued in 1935 that such instantaneous coordination was impossible, that it violated the deepest principle of relativity, that no influence may travel faster than light. Surely, they reasoned, the particles must have carried definite properties all along, secret instructions fixed at the moment of their parting, hidden variables that merely appeared to be decided at the instant of measurement. The correlation was no mystery, they suggested, but a kind of cosmic bookkeeping, like a pair of gloves separated into two boxes. Open one and find the left glove, and you know at once the other box holds the right, though nothing has passed between them. For 30 years, the question seemed purely philosophical, beyond the reach of any experiment. Then came John Bell. In a few pages of luminous reasoning, Bell showed that Einstein's comforting picture made a prediction that differed, measurably, from the prediction of quantum mechanics. If the particles carried hidden instructions, the correlations between distant measurements could never exceed a certain limit. Quantum mechanics predicted correlations that shattered that limit. Here at last was a question nature herself could answer, and when the experiments were performed, by Clauser, by Aspect, by a lengthening line of ever more careful hands, nature spoke without ambiguity. The hidden variables do not exist. The correlations are real, and they are stronger than any local explanation permits. Two entangled particles behave as a single indivisible whole, however far apart we carry them. This does not, it must be said, allow us to send signals faster than light. The outcome of each individual measurement remains random, and only by comparing notes afterward, through ordinary channels no faster than light, do the correlations reveal themselves. But the lesson is staggering nonetheless. The universe is not woven from separate, self-contained pieces. At its foundations, it is stitched together by connections that pay no heed to distance. Connections Einstein himself helped to reveal, even as he refused, to the end of his days, to believe in them. At the heart of quantum mechanics lies the wave function, a mathematical object that predicts, with perfect precision, the probabilities of where a particle might be found. It spreads out through configuration space, encompassing all possible positions, all possible momenta, all possible futures at once. Yet the wave function itself cannot be directly observed. We can calculate it. We can use it to make astonishingly accurate predictions, but we can never see it directly, never hold it up to the light and examine its features. It remains forever hidden behind a kind of veil, a ghost that leaves footprints everywhere but can never itself be caught. The moment we make a measurement, the wave function collapses. A single outcome crystallizes from the haze of possibilities, and all the others vanish as though they never existed. This measurement problem has haunted quantum mechanics since its earliest days. What counts as a measurement? Does a photon bouncing off an electron count, even if no human being is there to record the result? Does a Geiger counter count? Where is the line drawn between the fuzzy quantum world and the definite classical world we inhabit? But an even deeper puzzle emerges when we push toward the smallest conceivable scales. The Heisenberg uncertainty principle tells us that certain pairs of properties cannot both be known with arbitrary precision. The more exactly we pin down a particle's position, the less we can say about its momentum. This is not a flaw in our instruments, not a limitation that some clever innovation might one day overcome. It is how nature works at its foundations. And when we combine this insight with general relativity, something remarkable happens. If we attempt to measure distances smaller than the Planck length, roughly a trillionth of a trillionth of a trillionth of a centimeter, we confront an impossible requirement. Such measurements demand an amount of energy so vast, concentrated in a region so minuscule, that a black hole would spontaneously form. The act of looking would create a gravitational monster that swallows our experiment whole, enclosing the very space we hope to probe behind an event horizon from which no information can escape. The same constraint applies to time. The Planck time is the interval required for light to traverse the Planck length, roughly 10 to the minus 43 seconds. It is the briefest imaginable moment, the shortest tick of the cosmic clock. To measure a shorter interval would require energies so concentrated that, once again, a black hole would erupt into being. Time itself may have a smallest meaningful increment, a fundamental grain beneath which there is no before and no after, only a kind of smear where the very concept of duration loses its grip. The universe appears to have a built-in resolution limit, a fundamental graininess beneath which the very concepts of space and time may cease to have meaning. And so our two greatest theories, each spectacularly successful in its own domain, collide at these boundaries. Perhaps the way forward lies not in measuring reality more precisely, but in reconsidering what particles actually do when we are not watching. The story goes that Richard Feynman once posed a thought experiment to his students. What would happen, he asked, if you kept adding slits to the barrier? Not 2, not 10, but hundreds, thousands, until the barrier became more gap than wall, until the very concept of a barrier dissolved into an infinite series of openings. This apocryphal tale, whether it happened exactly so or not, leads to one of the strangest insights in all of physics. For when you extend the double-slit logic to its ultimate conclusion, the interference pattern does not vanish into randomness. The particle must somehow explore every possible path between the source and the detector. Not just the obvious routes, but all of them. Paths that detour through distant regions of space. Paths that zigzag wildly. Paths that seem to double back or spiral without purpose. Each trajectory contributes its amplitude to the final sum, its phase spinning like a tiny stopwatch hand. The improbable paths cancel each other out, their phases interfering destructively, while the probable ones reinforce. What survives in the mathematics is the classical trajectory, the path of least action that Newton would have predicted. But here is the essential mystery. We never see these paths directly. The instant we try to observe which route the particle actually took, the quantum superposition collapses. The exploration through infinite possibilities vanishes, replaced by a single classical fact. We are left with equations that work spectacularly well, predictions that match experiment to unprecedented precision, and yet we cannot say with certainty what the particle is actually doing when we are not watching. To understand that, we would need to calculate all those bizarre trajectories, one by one, and see what the mathematics reveals. So we begin the calculation. We must account for every possible path between 2 points. not merely the reasonable trajectories that classical physics would endorse, but every journey a particle might conceivably take, no matter how outlandish. The logic of the double-slit experiment, extended to its ultimate conclusion, demands nothing less. Consider for a moment what this means. A photon traveling from a source to a detector could take the direct route, the shortest path that common sense predicts. But it could also wander far to the left, loop through distant regions of space, or detour through corners of the cosmos that seem entirely irrelevant to its journey. Along the way, it might race ahead at impossible speeds, then slow to a crawl, then reverse direction entirely before arriving at its destination. The trajectories are bizarre, varying wildly in both speed and direction, and we must calculate every single one of them. When we perform this sum over paths, when we add together this infinity of strange and wandering contributions, something remarkable emerges. The phases of the wilder paths spin in such a way that they cancel one another out, their contributions interfering destructively, while certain routes reinforce constructively. The result matches experiment with spectacular precision. But the method that works so well in our equations leaves us with an unsettling question. If we must account for every possible trajectory to predict where a particle will arrive, does this mean the particle truly explores all these paths? Or is our mathematics merely a convenient fiction? Whether the mathematics of infinite paths describes something real or merely predicts what we observe, the question points us toward a deeper mystery. The two pillars of modern physics, general relativity and quantum mechanics, stand in fundamental contradiction. One path toward resolution, loop quantum gravity, seeks to bring Einstein's geometry into the quantum fold. But another approach reaches still deeper. String theory, the proposition that space and time themselves are not fundamental, but emerge from a more primal reality. In this conception, the ultimate constituents of nature are not particles, but infinitesimally small vibrating strings, filaments of energy a billion times smaller than an atomic nucleus, whose different modes of oscillation correspond to the particles we observe. An electron is a string vibrating one way, a photon another, a quark yet another. And among the harmonics of these strings lies the graviton, the quantum carrier of gravity, the bridge between Einstein's smooth geometry and the jittery quantum realm. If this vision is correct, then space and time are not the arena in which physics happens, but part of the performance itself, derived properties emerging from the collective vibration of countless strings, like the wetness of water emerging from the interaction of countless molecules. The contradiction that has haunted physics for a century would dissolve, revealing that general relativity and quantum mechanics are shadows cast by a single, deeper truth. 100 years on, we stand in a curious position. We wield quantum mechanics with breathtaking precision, predicting the behavior of electrons and photons to more decimal places than any theory in history. Our transistors and lasers, our atomic clocks and imaging machines, all bear witness that the mathematics is right. And still we cannot agree on what it means, whether the wave function is a real physical thing or merely a ledger of our expectations, whether the world splits into countless branches at every measurement or collapses into one, whether reality waits upon our observation or proceeds serenely without us. That a theory so accurate should remain so mysterious is itself among the deepest facts we know. For now, the fracture endures. The theory that would unite all of nature remains undiscovered. But we will not stop searching. We are the universe's way of knowing itself, and the contradiction between our two greatest theories is not a wall, but a door, waiting for us to find the key.